There's a deep connection between electricity and magnetism. Whenever charge is moving, that creates a magnetic field in the vicinity of that moving charge. If we take our wire and we wrap it in a coil, that has the effect of concentrating or amplifying the magnetic field that exists inside the coil. We're going to get numbers that are larger or magnetic fields that are stronger than if we had the same wire in a straight line or not coiled at all. There's two parts defining the magnetic field inside a coil. The math part is we'll use an equation. The magnetic field inside a coil, the equation includes the permeability, the mu. That's a constant that tells us how strong the magnetic field is in a particular material. When we're working in air or a vacuum, the permeability number is that weird 4 pi times 10 to the negative 7. Then it's got funny units of Tesla meters per amp. The equation will give us the number part of the magnetic field. To get the direction, we're going to use a left-hand ruler, right-hand rule. For coils, we use the hitchhiker-shaped hand. For this one, our fingers will match the electricity. Oops. To match electricity, let's fix that up. When we get our fingers to match the direction the electricity is flowing, then our thumb points in the direction of the magnetic field. Of course, left hand is for negative flow, right hand for positive flow. All right, just fit. All right, let's try that. If we've got a current flowing through a coil as shown, I'm just going to quickly draw the coil. Instead of trying to use tools or find one online, I'll just sort of freehand it. Coils are often the wires wrapped around a soft metal core. That gives it a little bit of rigidity, so it's not going to fall apart or get squished. Also, the soft metal core has the effect of amplifying the magnetic field. Maybe as a kid you wrapped wire around a nail to make an electromagnet. The nail, being a soft metal, increased the strength of the magnetic field. I'm not going to draw the whole 100 loops, but here's roughly what our coil is going to look like. We'll deal with the number part first. That's just plugging into the equation. Mu n I all over L. Because it's wrapped around a metal, instead of using the permeability for air, we're going to use the number given. In this case, the number, I just kind of made it up, is that the metal amplifies or increases the permeability by a factor of 150. So we're going to take our 4 pi times 10 to the negative 7 number and increase it by 150 times. The question also says there's 100 loops. We've got 100, a current of 3, and all of that is in a length of 10 centimeters or 0.1 meters. You can double check on a calculator, but when I crunch that out, when I round it off to the nearest tenth, I get 0.6 Teslas. That takes care of the number part of it. Now we need to deal with the direction. The way that I've drawn it here, it's totally up to you, but if we think about left-hand rule and negative flow, the negatives leave the little terminal of the battery. When they get to the metal, they're going across the front of it from left to right and kind of tucking in on the right-hand side. So it's kind of going into the page on the right, popping out of the page on the left. It's hard to do this without being able to show you my hand, but when I get my hand so that my left hand, my fingers are poking into the page on the right-hand side of the core material, when I do that, my thumb is pointed down. So we get a magnetic field that's down. We could just say as shown, or down will work towards the bottom of the page. Some sort of vocabulary to show that we know our left-hand, right-hand rule to figure out the direction. That answers the question, but we can add a little bit more. Magnetic field lines kind of leak out. So they kind of point out of here, point out of here. They kind of get drawn into the other end to match the arrow. So they kind of look like that. There's some that even wrap all the way around, so we get that classic butterfly shape. That butterfly shape matches what we saw when we looked at the magnetic field of a bar magnet. Bar magnet, the magnetic field lines always point out of the North Pole and into the South Pole. So sometimes when given a coil, the coil will be labeled with a North Pole and a South Pole. The North Pole and South Pole reflect what kind of bar magnet orientation would give those field lines outside of the field. So outside of the coil, the magnetic field lines are pointing out of the North Pole and wrapping around into the South Pole. So the North Pole, in this case, is at the bottom where the magnetic field lines are coming out. The South Pole is at the top where the magnetic field lines are pointing in. We've always said when we talked about magnetic field lines, they always point from north to south. That's what's happening outside the magnet. But what's a little bit weird and sometimes bugs people is inside the magnet, they seem to be pointing from south to north. So if ever labeling a coil with a north and south pole, look at those magnetic field lines that are outside of the coil.